Hello, everybody. It's me again, James, and I just want to take some more time today to talk to you about mathematics and Zombini puzzles. Now, in the last episode, I went through the puzzles of the deep dark forest and talked about functions and vectors. And even before that, we did the three puzzles of the big, the bad, and the hungry, and we talked about sets and functions and rules and a little bit of logic. Now, today, I want to do the three puzzles of Who's Bayou. Now, Who's Bayou focuses more on sorting and searching for things intelligently. Now, there is mathematics related to finding solutions to problems quickly and sorting things by attributes. But looking at this puzzle, I feel like what it's trying to do is provide a little bit more of an intuition to how you might search for things intelligently, more than really defining it in a more rigorous manner. It's more something you pick up than anything else, at least in these puzzles, I think. And besides, I am not qualified to discuss the mathematics involved with sorting or searching. So instead, I think I'd like to take this time to talk a little bit about the mathematics of mathematics education in mathematics, and what mathematical thinking is. Hopefully this will be a little bit slower, calmer, more contemplative little episode. So let's get started. I turned off some of the sound effects because they can be a little bit irritating, although for some reason I still can't find how to turn off the frog sound effects. It's starting to make me more than a little upset, but sadly, there is nothing I can do about it. Now, how do I do this puzzle? Well, every log on this boat is a seat, and you have to arrange the Zoombinis on the logs so that every neighbor of a Zoombini shares at least one attribute with it. Like, let's say put this guy here. Then we could put this guy right here because he has a yellow nose. They share an attribute. But if instead I try to put this guy right here, they don't share any attributes, and the frog's gonna kick him off the boat. There you go. And this might not seem like a mathematical puzzle at first, but I'd like to assure you it is. In fact, I remember reading about one rather neat solution to the problem that involved a branch of math called graph theory, but I can't really talk about it here. I need some sort of whiteboard to jot notes on. Pardon that brief interruption. Now, but this is mathematical even without graph theory, because what you have to do is you have to observe patterns. You have to observe which Zoombinis share attributes, and, crucially, which ones do not, and then arrange them in an order. And believe it or not, that is an attribute of mathematical thinking. Finding things that do and don't fit a given problem, large or small, is mathematical. It requires the use of logic in order to fit pieces of information together. Sorting things, whether it be by color or by size or by really any other factor, is mathematical thinking. Mathematical thinking is something that comes to people very early. And indeed, it's something that we try to encourage through the use of baby toys and children's toys wherever possible. And people always ask, like, in classes, when will I use math in my life? And it's true that, like, lots of equations, like, you probably won't use the quadratic formula in your day-to-day life. But mathematics, taught well, isn't just about formulas. And I know I've said that before, because there's so much more to math than just equations. But further than that. Let's switch this one for that one. Haha, now we got it. But mathematics taught better isn't just equations and things to memorize. And it's not just studying abstract structures either, I don't think, like sets and vectors, even though I did talk about those before and I do find those very interesting. I believe math, at its heart, is using different basic tasks like pattern recognition, deductive and inductive reasoning, and other ways of just thinking about the world, or just thinking about a set of rules in order to solve problems. And I think I'll talk a little bit more about that on the next puzzle. Off we go. So, what do we have to do for this puzzle? Well, this puzzle's not too bad. What you have to do is you have to take a frog and set him down on one of the lily pads. And when you set them down on a lily pad that matches the symbol on their back, for example, this red one matches with the red lily pads. This one matches with lily pads with 2 fronds on them. And this one matches with lily pads with a flower on top. And when you do, they set off across the swamp to the other side, at least to the best of their ability, with a Zoombini on their back. And that's how they get across. And this involves mathematical thinking, but why? Well, I have to look at the different paths across the pond, the river, I should say. And I have to look at what frogs I have, because some of them will disappear over time, and I have to figure out which ones I can use and which ones I can't use. For example, this red one, I know I can use again because it works. This blue one, on the other hand, is useless because there's no blue path across the lake. Isn't worth anything to me. I'm not even going to bother looking at it anymore. By contrast, this yellow one, I know, will reach the other side and can carry still another Zoombini across. There we go. I'm observing patterns in the lily pads and using that to figure out which frogs I can use and where to put them and which ones to ignore. And this is very basic mathematical thinking, but it can extend to like further, harder variations of this problem where you have to use, say, a magic wand to switch the lily pads around, or where you have to set up the frogs so that they avoid crabs that are moving around to block their progress. Let's see. Well, there's no pink path across the lake. Already used yellow and red up. No blue path, and no light blue path. So the color frogs are all worthless at this juncture. But that's okay though, because if I look here, there's a path of boxes with X's on it to the other side of the lake. There we go. I'm just going to keep calling it a lake. Let's see, is there something else? There is. This little patch of X's will carry Zoombinis across just fine. Let's think of another example of mathematical thinking that you probably wouldn't think of as mathematical. Just the other day, my vacuum, well, not my vacuum, the vacuum in my house, was like breaking down. It's just like it wasn't working very well, and my mom wanted to know why. Well, we took a look at it, and maybe it was the wheels. We checked the wheels rolled fine, so the wheels weren't the problem. We checked the filter was cleaned out, it was a-okay. We plugged it in or ran it, and it did make a noise, like the fans were whirring and everything, so it wasn't like the power supply was bad. And then we noticed a smell. The belt's burning. And we realized that part of the reason why the vacuum wasn't working as well as it could is because the belt had worn out. And that's mathematical thinking. You start with a problem, like a vacuum not working as well as it should, and you work through different approaches until you find a solution to a problem. You can check different possibilities, and then you use logic to prove or disprove each one, along with your own observations and patterns. We didn't even really need to look at the vacuum's belt to know it's worn out. Why? Because there's a pattern. We already know what a burning belt on a vacuum smells like. So, we can just say, yep, that's the belt. And we can be reasonably sure that it's the case. Of course, that's not very rigorous reasoning. But in such cases like this, it doesn't matter too terribly much. Let's see. Oh, look at that. There's a path of flowers. We can use that, can't we? And that's just one example. When I prove a math problem in school, I kind of do the same thing. I start with a problem. Let's say, prove that there's an infinite number of primes. And I can think about different ways I might go about proving that. Maybe I'll try and prove it directly. Just saying, okay, here's what we know, and here's why that means there's an infinite number of primes. Maybe it means proving it by contradiction. Okay, assume there's not an infinite number of primes. Does that make anything go wrong? If something goes wrong, then there must be an infinite number of primes after all. Maybe I prove it by induction, where I prove it for some small case and then show that that small case builds up to bigger and bigger and bigger cases. All of those are mathematical reasoning, and all of them are kind of similar to something you may use in a real experience in your life. And that's something that I think is important. I think that's something that's overlooked. When you teach people to memorize, when you teach to exams, I feel like it's very easy to miss mathematical thinking that people will use in everyday lives, like refining their ability to use logic to solve problems. And just, we're all out of symbols. Well, lily pads it is. But refining their ability to use logic to solve problems and refining their ability to think about problems and solve them. I know I'm a bit of a broken record, I'm afraid, but I just feel very passionately about this, and this is a dead end. Let's see. Let's try... Oh, would you look at that? 4-leaf will lead you right across. Well, not right across, but close enough. But that's what I think mathematical thinking is. Just observing things and using patterns to solve problems through reasoning. And it is something you do every day. Whether you think you do or not, you do use mathematical thinking. Maybe it's trying to figure out if something's cheaper at one place than another place. That'd be very concrete calculations, or calculating a tip. Or maybe it's just trying to figure out what's going wrong when you're not quite sure what the error might be. That's mathematical thinking too, and it's absolutely as valid as anything else. Pardon me. And that's part of why mathematics is important, because it is something that you use constantly. Even if you don't think about it, thinking that is mathematical in nature is something everyone does eventually. You can't really avoid it. But another reason why I enjoy math is because math is a fundamentally creative and beautiful field. And I know lots of people probably think that's kind of crazy when I say that, and I can recognize that it seems a little bit off-putting, but I think that's another thing that we miss a lot with math education. Okay. Here's a little... There we go. Okay, so let me just check to be sure. Yep. Off you go. But I feel like it's something else we miss a lot with, like, teaching with emphasis on memorization and teaching the tests. is that mathematics can be beautiful and creative. Like the thing I just mentioned about proving that all of the prime numbers that there's an infinite number of prime numbers. That's something that you can approach in a variety of different ways, and people have done it many different ways over the years. Each way they do it reflects different fields they may be working in, different values, different approaches, different ways of thinking. A mathematical proof isn't just a product of the rules of mathematics, but it's also a product of its author. I remember one definition of art that I like, and some people may think it's too vague, but I enjoy it, is that art is anything with anything with human design put into it. And maybe that's a little too wide, but under that definition, mathematics is absolutely an art form, because any proof at all, good or bad, will require human design. Okay, so we know this little guy won't take you anywhere. So therefore, the only one that works is this three-pronged guy. So let's see. Sorry if I get a little lectury. Just the philosophy of math and teaching it is really important to me. Ooh, exciting. There you go. And he's off. And math can be beautiful, too. Like, if math can be creative, then certainly I imagine it can be beautiful. Some people may scoff at that, but it is. I remember one of my mathematical heroes, Paul Erdős, God bless him, had this concept of a thing called the book. And in the book, he said were stored all of the greatest proofs that mankind would ever, all the greatest proofs of math. Not even mankind, but just the greatest proofs, period. Things that were beautiful and creative, things that were elegant, things that assumed little and yet proved much. And I've certainly heard a few proofs that fit into that, and I just find them absolutely marvelous. And it is something that requires a little bit of getting into. It is something where where literacy in the language is more than a bit required. But it still is fascinating to see a proof and to recognize how it works and the amount of creativity in the thought that created it. I suppose one of the ways I might describe the beauty of mathematics, especially when it comes to proofs, which I enjoy, is it's like the beauty of a sonnet or a haiku. Of course, the contents of the proof are interesting and beautiful, just as the words in the verses of a haiku or sonnet are. But what makes it even more impressive is the rules that it operates under. Just as a haiku and a sonnet have syllabic structures, and sonnets have rhyming schemes, very intricate ones at that, mathematical proofs operate under certain rules and require certain levels of rigor. You have to prove things step by step by step, and in doing so, you take something that you weren't sure was true, and then you demonstrate it to be an absolute fact under certain assumptions. The rules don't ruin it at all. The rules of mathematics are in fact part of what makes it fascinating, because you realize people have to work within them in order to prove things. Sometimes absolutely mind-bending things. Gödel, a noted logician of the 20th century, proved that no matter how you create a logical system, if it has a certain level of complexity, it will contain statements that are true, but you can never, ever, ever prove. And he proved that with logic, with mathematical thinking. And that's a very brief example, and that's just like a very brief description of it, and it's nowhere near complete. It's probably not even a very good description. But it is something that is fascinating to think about, and I'd love to talk about more once I get a better handle on it myself. Let's get on to the next puzzle, though. I'm sure I'll spend more time in the future talking about mathematical beauty. I'll probably throw up a little video right now or so about a mathematically beautiful thing I enjoy. Check the corner. What I want to do for this last puzzle, well, first I should explain it. Each of these little two hexagons linked together are connected by a tile with an attribute on it. In this case, an eye. So what I have to do is I have to place two Zoombinis here that have the same eye type, and the feet type, and the nose type, and all these other ones. And eventually, when they're all on board, I click this little green arrow, and they move on. So let's get started. Let's see, are there any eye types right off the gate that we know can't work, that we don't have two of? Well, sunglasses, we have two of sunglasses, we have two cyclops, we have two dot eyes. Huh. So yeah, we can't really rule out any eye types. What about nose types? We have two greens, we have two blues, we have two pinks, we have two yellows, we have two reds. So yeah, any of the eye types can fit these either. Well, any of the eye types and any of the nose types can fit these. What about feet? Do we have any feet we can rule out? We have 3 wheels, 4 roller skates, 3... yeah. So there's nothing we can really rule out directly right now. For example, if there's only one Zoombini with a single eye, then we know a single eye Zoombini couldn't go in any of the eye slots because it wouldn't have a partner. Alas, we cannot do that here. Nonetheless, you must continue forward. One last thing I'd like to talk about is education and a problem I have with public school and mathematics as it's currently taught. And this is actually kind of ironic because what I want to talk about has something to do actually. Oops. Also, don't drop it on any of these other hexagons or else the Zoombini will be zapped with electricity and shot into the sky. Fun fact. But like I was saying, I think it's funny because what I want to talk about with regards to education actually deals with both math and computer science. And as it turns out, my father and my mother are, at present, math and computer science teachers at a public high school currently. I think it's hilarious that someone in the future might ask, "Oh, so did you become a math professor like because your dad was a math teacher?" Actually, he only became a math teacher after I started my math major. It was entirely unrelated. But I just think that's hilarious. Anywho, it's been a while since I've been in public school. It's been 3 years, soon be 4. But it's been a while, but I remember there being a massive push for more computer science education. For just like, kids need to learn how to program, kids need to learn how tech works. And if I may interject, and I see no reason why I shouldn't be able to as a product of public school, I think it kind of misses the point. Now, kids should learn to program, but it doesn't matter what language they learn, and it doesn't really matter how they learn it, because what programming really is it's a class in mathematical thinking. Red nose. Haha. Fixed. But yeah, before I wrap this up, I'll just talk a little bit quickly. Programming is just applying mathematical thinking. When you write a computer program, you have to write precisely like you would in a mathematical proof, because a computer can only do exactly what you tell it to do. It can't interpret what you mean the way a human can. When you write a program, you may need to look for patterns or observe how things work and then try and write a way to output what you want from that. You have to write instructions, which are mathematical too, and we can always talk about that in the next video, which does have a little bit to do with algorithms and instructions and everything else. But you also have to use logic, and you have to use things sometimes that are like sets, which contain data, or things like vectors. Programming is very much an exercise in mathematical thinking. And I think part of the problem is, with so much emphasis on tests and memorization in math classes now, we're not teaching children mathematical thinking. We're not emphasizing the parts of math that are useful and interesting and fun. We're not emphasizing those things, and so I believe this push for computer science and programming is really just a way of supplementing that. It's a way of doing something that we should have been doing all along. You don't need to program or to learn about computers to learn how to look for patterns or how to solve problems or to debug things or how to write clear, precise instructions or communicate well. Can it help? Absolutely. But all of those things should be taught earlier and taught more generally in mathematics courses. And I'm not sure what the face of that will be in the future. I'm not sure what the shape of math education will be even 5 or 10 years from now, especially not in public schools. But a truly successful math program, in my opinion, and my grossly unprofessional opinion, I should say, would be something that encourages creativity and encourages searching for patterns and observing for things, and then using that to learn about the world around you on its own. And that's part of something I've read about called the Moore method of teaching, which can be effective, although I'm a little bit split on it. But maybe if you guys want to hear about that, I can talk about that later. I'm not sure. But I think it's time for Zoombinis to move on, and I think it's time for me to wrap up this episode of Math and Zoombinis. Thank you all for watching my tireless ramblings. Have a lovely night.